This is Surveying 1, Lecture 15, and in this lecture we're going to cover some of the discussion involving field measurement of angles very specifically. So I'm going to start by talking about how you set up. So to set up, as you probably know, we need to have a tripod and we need to have an instrument that sits on the tripod. But don't forget that we also need the targets, whatever it is that we're going to observe, to be able to measure the angles. And there's a whole variety of them, and I'll talk about them a little bit. But let me first talk about the setting up procedure. We will spend a lot more time on this with other videos and with the labs, or we actually do field demonstrations. But I just want to go through this because I don't think there is such a thing as saying this stuff about setting up too much. Because if you are new to setting up an instrument over a point, it will take you several tries, and listening very carefully and paying attention to these instructions will make life a lot less painful. So to do this, the first thing you do is you use the optical plummet of the instrument. So there's an eyepiece on the LED of the instrument that you look through. It strikes a prism, and then your line of sight is projected downward through the center of the instrument. So the axis of the instrument is hollow. And it allows you to see the point on the ground that your instrument is centered on. The thing you have to remember here is that the instrument is designed so that the optical plummet projects out along the vertical axis of the instrument. But if the axis of the instrument is not level, then it's going to be pointing along a direction that's not truly vertical. You need to remember that. So when you start the setting up process, you start by first getting the crosshairs inside what we call the optical plummet on the point on the ground that you need to be over. And that may result in being inclined a little bit. I'm exaggerating it here. So you're not actually over the point, because to be over the point you need to be like this, but instead you're over here. And then what you do is you adjust the legs of the tripod. So you observe the level bubble, the circular level bubble on the instrument, not any other bubble. You observe the circular bubble level. The instrument is on the point, but it's not level. And now you shorten or lengthen the tripod legs, and there's a little bit of technique that we'll go over in the field demonstration to get the instrument leveled by shortening and lengthening the legs. What that does is it tends to move the instrument but keep the optical plummet crosshair more or less on the point. It'll drift off a little bit, but not that much. Then when it's centered approximately on that nail or whatever it is on the ground, you can use the leveling screws to level up the instrument. So then, just to point out, here on the right-hand side of my slide, I have steps 1, 2, and 3. I've repeated steps 1, 2, and 3 on this next slide, and then added 4. So how well you approximately center to start off with will determine how far your optical plummet will be off when the point will be off the point when you're finished with step 3. So you do have to pay some attention. You can't be too sloppy with steps 1, 2, and 3. Now let's move on to step 5. There's what's called the tripod fixing screw that holds the instrument clamped to the tripod. You loosen it just a little bit, half a turn maybe, and you can now slide the instrument on the head of the tripod without worrying about the instrument falling off the tripod. And you can re-observe the optical plummet to make sure that the crosshairs are back on the ground point. Now you clamp it and re-level the instrument. Then you go back and recenter. So you loosen the tripod fixing screw, and you recenter again, and then you re-level. And for some of you, you may be doing this 5 or 6 times, because when you're new, it turns out there's a lot of skill in following these procedures to be able to do it quickly and easily and accurately. And so what I say here at the end is that experts can set up accurately in about 2 iterations of this back and forth process between loosening the tripod fixing screw, moving the instrument to recenter on the point, and then re-leveling. It might take 2. With novices, it may take a few more. Now, there's a lot of fine points in how you do this that I'm glossing over for now, and in later videos and in the field demonstrations, we'll go into this in a lot more detail. So it's really important to be paying attention. So once you have the instrument leveled on the point and centered, so it needs to be level and centered. It's not enough to just have one of them, you need to have both. Now you can power up the instrument. And what you do is you back sight your first point. And then you have a function on your instrument that's called the zero set. It can set the angular value, the horizontal angle value, to 0. However, once you hit the 0 set, just the action of pressing the 0 set button may cause the instrument to move off the point. Having an extremely light touch is a really important part of measuring angles once you have the tripod and the instrument properly set up. So that's why I said after you hit the 0 set button, you re-sight the target, meaning you look through the telescope and use what we call the tangent screw. You are familiar with this term from using the level, to re-center your crosshairs exactly on the target. But in the process of doing this, you may not be reading 0 degrees, 0 minutes, 0 seconds on that backside point. Now you could hit the 0 set button if you wanted to, but what I found with new students especially is that you never finish then, because every time you hit the 0 set button, you throw the instrument a little bit off your target, you re-center on the target, and now you're not reading 0 degrees. So what I tell people is you do what I said here. You 0 set, you re-sight the target because it may have moved off a little bit, and then you record your reading, which may be a small value, such as 0 degrees, 0 minutes, 2 seconds, or 0 degrees, 0 minutes, 5 seconds, or it could even be 359 degrees, 59 minutes, 57 seconds, which would be the equivalent of -3 seconds. Now you turn, and there's a whole bunch of manipulations of the instrument that have to be done that I'm not going to go into here, but I'll demonstrate here shortly. And as I said in other videos and in the field, now you turn to the foresight target and sight at it, properly center your crosshairs on the target, and record it. Now, the angle between the 2 lines that you measured between your back sight and your foresight. So you have your back sight, and you have your foresight sight. So you had something near 0 on your back sight, and you have whatever you have on your foresight. Taking the difference between those 2 values gives you what this total angle is. Now, that means you measured the angle once in what we call phase 1. Now you invert the telescope, go back to the back sight, and exactly repeat these steps. So you sight the back sight target, and then you go to steps 4 and 5, which is to record the reading on the back sight, and then turn to the foresight, and then record that reading as well. So now you have 2 angles, one in phase 1, one in phase 2. Don't be surprised if they're not exactly the same, because it depends on a lot of things, not just your skill. The instrument could be slightly out of adjustment as well. And so now you average those 2 values to get the value of the angle. So let's talk a little bit about targets. And to do that, we start by talking about the kinds of reticles that might be in your instrument. Your instrument is likely to have a reticle similar to the pattern shown here in part E. But these are some of the other reticles that you might see in the instrument. So there's a There's a dominant vertical axis, there's a dominant horizontal axis. And then there's a whole bunch of other lines which are in different places doing different things. One pattern that I have seen sometimes is that there's a little circle in the middle. This dot is not on your radical pattern. That dot is simply placed there by whoever drew these radical patterns to tell you that's the intersection of the horizontal and vertical crosshairs. And so one of the things you need to realize is that you can be sighting different kinds of targets, and sometimes you have to be selective about it. So one of the things you will be doing is sighting at prism poles that are held on points that you wish to measure the angles between. So let me get this prism pole and just talk about this a little bit. There's a lot that needs to be thought about when you measure an angle, and then for now let's just say horizontal angles. First of all, you need to make sure that the person holding the prism pole is properly holding the prism pole with the circular bubble centered. If they're not holding it centered, if it's being held at an angle, obviously you're not going to be measuring a horizontal angle very accurately, because the whole idea is to place the vertical crosshair in such a way that the vertical line, as you're observing the target, passes through the ground point. So there's several places you can sight at. So you notice around the prism you have these triangles. So one of the things you can do is place the vertical crosshair exactly on the triangles that form the apex of each triangle. And these triangles are supposed to be exactly opposing. So you can look at the upper triangle, the lower triangle, or perhaps both. And just as while I'm at it, if you're measuring vertical angles, then it's the horizontal crosshair that's important. And of course, you would do the same thing. You would place the horizontal crosshair exactly at the apex, which happens to be, there's a plastic rib, so it's orange. So the apex is actually obscured a little bit. However, there are times when it makes more sense to actually observe some other place on the prism pole. The one thing I don't encourage you to do is to place the crosshairs so that the prism, meaning the circular object that is the prism, is exactly cut in half. Or if you look inside the prism, you see something that looks like a star-shaped pattern. Do not place the crosshair on that star-shaped pattern, because if you do a little experiment, you'll see that depending on how the prism is pointed at the instrument, the star-shaped pattern actually moves to the right and to the left. So you don't want to sight at it. There are some optical things going on that we'll discuss in surveying too. And this is a very common blunder committed by surveyors today, because they don't understand this little problem. And all you have to do is do a little experiment where you hold the prism pole very carefully, or you mount it on a tripod, or some other way to hold it stably, and then you simply rotate the pole and you'll actually see this prism shift laterally by quite a few millimeters, which means it's changing the angle value that you would record. So there are other things you can do, because one of the things you need to think about is how far away is this prism and this target surrounding it from you. Because if it's very close, you may see a lot of apparent movement because the instrument is so close to you and you're looking through roughly a 30-power telescope. So you may have to do other things. And so I'm going to talk about that here in a second, or in a slide or two. The other thing that you can think about is sometimes you're so far away that you can actually bisect the width of the pole, cut it in half with the vertical crosshair. However, when you do that, don't sight at this silver part, this chrome part, because you can have something known as phase error. Most surveyors have no idea what this means, but I would strongly suggest you look at other books, because your book that we're using in this class doesn't cover it. But phase error is basically where, because of reflection, now I'm in a studio, this could be the sun, you have a brighter side over here, and this brighter side will cause the shape from a certain distance to look narrower than it is. And so when you set your crosshair to be centered on this chrome part of the pole, you might not actually be centered. You can see now in this little close-up, because of the intense light being reflected from this point here, that what you see may not be the full width of the pole. And the whole idea is to be able to center the crosshair on the full width of the pole. So don't use a highly reflective part. So what I'm going to do now is lift this up, and you can see, because it's painted, you're less likely to have phase error. It's one of the problems of having a telescopic pole. Telescopic poles are a great idea because you can have a really tall pole when you're sighting a long distance away. But as you can see here, you still see some of the reflection that was causing the problem when you're looking at the chrome part of the pole, but it has much less of an effect. And that's the other reason why I wanted to show you this, because it's painted in alternating bands of white and red. And so one of the things you should do is check, place the crosshair maybe where the horizontal crosshair goes across right here, so that you can see if the vertical crosshair bisects the white part and the red part the same way, because you may be having phase error with one of these two, depending on the color, on the background, on the lighting. There's a whole bunch of things that can happen. And finally, I'm just going to turn this pole upside down. If you are very close and you're setting points, say to stake out something for building construction, and you can actually see the point of the prism pole, keep in mind it's inverted so it's on the ground, something you shouldn't be afraid to do for angle measurement is actually sight on the tip of the pole, on the point of the pole, if you can see it. So you have a lot of choices, and don't assume, because remember with the total station you will be measuring distances, so there will be some point at which you actually center at the prism so that you can properly make a good distance measurement. But that may not be the best place to sight to get a good horizontal angle reading as well. So it's something that you should definitely keep in mind. Now here are some of the other types of targets. You see the prism pole, of course, pictured at extreme right, but we have these other kinds of targets. I showed you the target that we have surrounding our prism. You notice there's different patterns and different sizes. For example, in the middle picture, the prism that's shown on the right side of that middle picture is probably designed for close range work because that pattern is quite small. Whereas that yellow prism holder in the middle is even bigger than the one to the left of it, so it's probably designed for work that's further out. Now, there are some issues with this particular target, and that is that you notice that where in the target to the left of it, we have a very clear light triangle on the black background for the vertical crosshair. We only have one, and then you have two for the horizontal crosshair, and yet on a black background. Here we have something different, and look at this very carefully. We have here a yellow triangle with a black background. But for the horizontal crosshair, we have a black triangle on a yellow background. And in my opinion, that's not as good a technique for designing a target pattern. You're much better off having the same kind of contrast. And then here's on the extreme left something called a traverse target. This is actually designed to be even used at night. You may see a wire if you look at this closely. So it's actually possible to light the white part of the target so you can even observe this at night. And if you look very carefully, you'll see that these triangles, both the triangle for the vertical crosshair as well as the two smaller triangles for the horizontal crosshair, that at the very apex you have a slight narrow channel. And the idea in having that is that if you are observing this target extremely close range, you may be able to place the crosshair inside that little narrow channel because you're that close to the target. And so a lot of these targets, this triangular pattern is designed so that you can sight it from a great distance away as well as a more close-up observation. Now, one of the mistakes that people make is to assume that whether it's a prism with the triangular targets like this, and then a pole down here, or those traverse targets and so forth, that the purpose is to place the vertical crosshair, and you remember the vertical crosshair in most of these instruments doesn't look like this. Instead, what you have is a double line that comes to a cross, and then a single line going up and down as well as right to left. And there's a reason for this. You actually have three choices. If you can see everything about the target up close, you can place the cross in the middle of the reticle. Reticle is often the name given to the pattern because the reticle is basically etched onto a piece of glass somewhere in the telescope, and it's overlaid on the image you're looking at out there. But then you can use the single crosshair to place your crosshairs directly on the apex of the instrument. But there are times when it turns out that it becomes more appropriate to place the double crosshair on the triangle. Why? Because if you look at this very carefully, and I've just hand drawn this, you can see where the double crosshair on the left side crosses the side of the triangle there, and you can see where the double crosshair crosses the side of the triangle here. You can see where they're not at the same height. And if I moved this instrument a little bit, moved the reticle a little bit more to the right, I think you can see how the arrow would drop down, and the whole idea is to look at the symmetry in how the double crosshair intersects with the target to be able to really tell that you're properly centered. And this is a function of how far you are away from the target as well as the level of light. So if you're on a very dark, gloomy day, or you're working indoors and the target is not very well lit, you may discover that one style of crosshair, meaning the single or the double, works better on a particular target than another one. And then finally, another reason for having the single and the cross double is that if you're real close to the target and you decide you've got too many issues, and sometimes people will mount a prism on a prism pole without the surrounding target with the triangle. Those people, by the way, the people who do that are probably the biggest offenders of putting the crosshair directly on that star-like thing on the middle of the prism, which is a big mistake. What you're better off doing for horizontal angles, if you're up close, is to put that single crosshair where it bisects your prism pole. But if you're far away, what happens is the thickness of the pole appears to get smaller and smaller and smaller and approach the width of the crosshair. Once the apparent width of the pole and the apparent width of the vertical crosshair are roughly the same, trying to superimpose the single crosshair on the pole can cause angular error because the prism pole in effect is hiding behind the single crosshair. That's when you use the double crosshair, and instead, so at a great distance, this prism pole will not have this apparent width. It'll just look like a fine line. And what you can then do is place your double crosshair on either side of that fine line such that the space between your double crosshairs is split exactly. Now, if you're only measuring angles to the nearest minute, this is not very critical, but there are many times when getting the absolute highest accuracy in pointing at your target needs to be thought about, and that means you need to think about which part of the reticle you use, how well your targets are lit, and what types of targets you're using. There are times when you might pull out something like the traverse target. That's the object I have over here on the left-hand side as a way of making much better observations than you could with other types of targets. So one of the early procedures that you'll be following when you get to angle measurement, when you first get your hands on the instrument, is do an exercise called closing the horizon. So let me draw on the sketch here a little picture. What you will do is you will set up your instrument on a point, and most of the time you pick 3 targets out there that you're going to observe. And what you do, let me just number them, so points 1, 2, and 3. The instrument is set up at point 4. And what you do is you backside 1, you foresight 2, you measure that angle. You backside 2, you foresight 3, you measure that angle. And finally, you backside 3, you foresight 1, you measure that angle. And those 3 angles should be adding up to 360 degrees. So this is a good way of evaluating your skill in measuring angles, because you know perfection would be 360. And so what I want you to do is to learn how to do this and to learn how to do it by measuring in phase 1 and in phase 2. So I'm going to go through that process just very briefly, kind of walk through it. Here's the surveying instrument, and the table I have on the board essentially is duplicating the columns that we would have, that we would use to record our angles. Now keep in mind that we are taking a backside reading on one target, a foresight reading on another target. We compute the angle by taking the difference between the two of them. We do that in phase 1, we do that in phase 2, and then we average them. So if you look at the instrument, just to point out a few things on the instrument, you should by now have seen the introductory video to the instrumentation, but we have several things. First of all, we have the angle fixing clamp, which is down here underneath the tripod, and this allows me to move the instrument around on the head of the tripod, and as long as you haven't unscrewed the screw totally, without fear of the instrument falling off. And so I'm going to reclamp it now. Don't reclamp it tightly, just want it enough where you cannot move it. Here is the eyepiece for the optical plummet. So basically it's what we call a folded telescope. When you look through this optical plummet, your line of sight goes to the middle of the instrument, hits a prism, and then gets projected downward. And then over here is a second knob, and this knob is used to bring the nail or whatever it is on the ground into focus. So this focuses the crosshairs, this focuses the objective, and just like with all the other telescopes that you'll be using, and we've already discussed this with levels, so I'm not going to talk about how you do it or why you do it, but you need to eliminate parallax, and you need to learn how to do that. The next thing you do is you look at the eyepiece, and you have the eyepiece focusing knob over here that focuses the crosshairs, And then the objective focusing is this big ring, so you eliminate parallax there. So those are two of the first things you do once you have the instrument set up and leveled over the point. Actually, you get parallax eliminated on the optical plummet before you even level and center on the point. But before you start making observations, you want to remove parallax on the main telescope of the instrument as well. This particular instrument has two displays and keyboards. So how can you tell whether it's in phase 1 or phase 2? Well, there's a couple of different ways. One is when you switch it on and you have the instrument roughly horizontal, look to see if the vertical angle is roughly 90 degrees. That'll tell you if the instrument is in phase 1. There is a bubble for leveling up the instrument. It's called the plate bubble or the main bubble, which is a lot more sensitive than the circular bubble, which is over here at the base of the instrument. And then you have these knobs that control this rotation. So this particular knob over here is used to lock the instrument to keep it from moving side to side. It's the outer knob, the bigger knob, and the smaller knob then is the equivalent of the tangent screw that allows small movement right and left. And then over here on this side is a similar arrangement, and this one here is for the vertical motion. So this motion of the telescope is fixed using the outer knob over there, and then once that's fixed you can turn, let me lock this just to be on the safe side, and then you can turn the tangent screw to move the telescope up and down. And I don't know if you can see that in this particular view, but that's what I'm doing. I'm elevating the telescope in a very controlled fashion. For your purposes, you shouldn't have to ever remove the handle, so please leave it alone. There is what we call a peep sight or a collimator sight. So there's a sight at the top of the telescope. Keep in mind there's an electronic distance meter. That's why it doesn't look like a conventional telescope, nice and slim. There's a peep sight over here. So when you're ready to observe a point, you can always look with both eyes open and get the instrument roughly lined up before you clamp everything down, because chances are, especially when you're new at this, you clamp it down, you look through and you don't see anything. Well, it may not be focused properly, or it may be that you missed, and so now you have to do some hunting, and it helps when you first start to actually do this with two hands, but you do it very gently. You do not place any weight on the tripod or on the instrument as you do it, and you certainly don't make measurements holding the tripod as I am right now. It's fine in the early stages when you're trying to set up the instrument to touch the tripod, but once you're finished, you're satisfied that the instrument is set up and leveled, you don't touch the tripod, you only touch the controls that are needed, which could be the eyepiece or the objective focusing for the optical plummet, same kinds of controls for the main telescope, what we call the horizontal motion clamp and the tangent motion, and then the vertical motion clamp and the vertical tangent screw. And that's pretty much it. Everything else you should be very careful. Do not ever touch the precise bubble that's located on the instrument, because it's quite sensitive and can go out of adjustment. And of course, when you're setting up the instrument, you have 3 leveling screws on the base, similar to what you had with the automatic levels for leveling up the instrument. So to go through this process, so let's say we are at station 4, and we're going to backside 2 and then foresight 3. So what we would do in our field book is write angle 2, 4, 3. And if you want to, you could put dashes in between them. What this means is the middle number is always where I am set up. 2 is my backside, 3 is my foresight. And so as I said earlier, what you do is you sight the back sight, and once you have found it, you get everything into focus, make sure no parallax, you clamp the horizontal motion, you clamp the vertical motion, and then you use your tangent screws to get your crosshair properly oriented on the target. At that point you hit zero set, and as I said, zero set has a tendency to move the instrument slightly off the target, so you immediately go back to the telescope and you you might need to touch up the pointing of the crosshair, and when you do that you may discover you're not reading zero anymore, which is fine, so you record that value. And I'm going to say that the value I recorded was 359, 59, 57. Now, hopefully you can do this math, because one of the things I recommend you do, if it's a small angle like that and you see 359, 59, 57, just record -3 seconds. That's totally acceptable. You should be able to do that simple math. Now what we do is we release the horizontal motion, we release the vertical motion, and we move to our foresight point. And by the way, when you do this, make sure you don't trip on the tripod leg, because if you do, then you have to start all over again. And I don't mean remeasuring the angle, you need to check your leveling and your centering. Once you find it, you lock down the horizontal motion, you lock down the vertical motion, you use your tangent screws to get it exactly on target, and then you read off the value. Now if you have a note keeper, you read off the value, and let's say it's 135, 47, 10. You notice I wrote 42, because these kinds of things do happen. So it's really important, if you call out 135, 47, 10, that you're looking at it, and as soon as the note keeper hears it, the note keeper should start writing, and as soon as they finished writing, they call it out. And they'll say 135, 42, 10. And you say, nope, it's not 42, it's 47. And so then the note keeper comes in here, strikes through the 2, writes a 7, and you go on with life. Now, what is the angle that's been measured? Remember, we started on the other side of 0 by 3 seconds. So our total angle here is 135, 47, 13. Now, you come back to the instrument, you release the upper and lower motion clamps, and now you invert the telescope. When you do that, make sure you don't touch the glass of the objective or the eyepiece. Go back to the back sight, and you repeat the process. Now keep in mind when you do this, now that your clamp is on the other side, away from you, and the vertical clamp will be on your side, and so you can fine point at the target, and once you have it, you press 0 set, and it may have moved off the target, so you look through and you readjust the sighting, and then you note what it is. Now when you notice I said hit 0 set, people don't always do that, but that's what I think is a valid way to do it. And it could be this time we read 000002, and of course this is angle 243 as well. And what I recommend is that you write F1 and F2 to indicate what it is that you're doing. Now keep in mind also that I'm using only 5 of the columns, so you could use a 5th column to record that. I'm actually reserving the 5th column for a different reason. I'm not using it here, but I'll talk about it more at length later on down the track. And now we observe the foresight. So I'm going to go through that process, observe the foresight, call out the number, and this time I get 135, and this time we get it correct. We write down 47, and we write down 15. So 135, 47, 15 minus 2 seconds gives us an angle of 135, 47, 13. That's some miracle. Both angles came out to be exactly the same. So our average, which I like to write on the line between the two, is 135, 47, 13. Now, keep in mind the 35 and the 47 are likely to be the same, although sometimes you might have, for example, 135, 47, 59, and 135, 135, 47, 59, and 135, 48, 03. So you have to be a little careful, but it's fine here if you want to just write the 13 seconds, and if you wanted to write the 4713, meaning that you get the degrees from coming back here and looking at it. Now you don't draw those circles and lines on your field book. I'm just showing you how that shorthand notation for calculating the averages is acceptable, because someone reading your field notes, once they understand what you're doing, will say, aha, I know that the average is 4713. And that's how you repeat this process. What I like to do is skip a line, so my next angle would be 341, and you repeat the same process. So this is how this works to be able to finish closing the horizon. You have 3 of these average angles, and then what you would show, and I don't have the space on the board, would show how you sum these angles up to check them and compare them at 360 degrees. So that's the basic process for closing the horizon, and just a little bit of a run through on how you make those measurements. And with that, we will conclude this lecture.